So in this video, we're going to go through the development of the ideal gas law and show how we can use it to calculate various properties of gases. So the ideal gas law is what we call an equation of state, and this is sort of the holy grail of what we want when we're studying materials properties, because it's an equation that allows us to predict the relationships between macroscopic or observable variables, such as pressure, volume, and temperature. So we can measure pressure and volume, we can predict the temperature. If we measure volume and temperature, we can predict the pressure. We can't do this for solids and liquids yet, but we can do it for gases. We're going to start out talking only about ideal gases, but we'll see that from that same equation of state, we can make a couple of very small modifications to describe real gases in a more accurate way. So this will be review for the 4 p.m. class, this entire video. These are things we've already talked about in class. And what we're going to see to start with is that this equation, this ideal gas law, was developed by observing gas behavior. So we're going to take this historical approach and look at what did people observe in their experiments that led to the equation. So if we start by looking at some container of gas molecules that has some pressure, volume, temperature, and number of moles of gas. So lowercase n always means number of moles. We'll put our little gas molecules in blue here. 1, 2, 3, 4, 5, 6. Let's put 6 in there. Okay, so there's our starting conditions. And the experiments that were used to develop the ideal gas law go as follows. If we keep the temperature and number of moles constant, so we've got some fixed amount of substance, we've got a constant temperature, and we decrease the volume. So if we make our box smaller with our 6 molecules in it, the observation is that the pressure is going to go up. So we've decreased the volume, but the pressure then went up. And so we see that volume is inversely proportional to pressure. And this is what we call Boyle's law. And I don't really care if you guys know the names of all of these laws, but the fellow that developed this set of experiments and that relationship went by the last name of Boyle. And remember that since we know pressure is equal to the force exerted by the molecules divided by the area over which they collide, clearly, if you make the volume smaller, but you have the same number of particles bouncing around, they're going to hit the walls more often, and this is what leads to the increased pressure. The next law we're going to look at, we're going to keep the pressure constant. So this would be like having a balloon, and so the pressure inside the balloon is going to be the same as the pressure outside of the balloon. The walls can expand and contract, and if we keep the pressure constant, but we increase the temperature, well, the balloon is going to expand. It's going to get bigger. And so we've got our same 6 molecules in there, but now they're hitting the walls faster because of this increased temperature. They're moving around faster, so they're hitting the walls more often, and so we see that the volume is directly proportional to the temperature. So if the temperature goes up, the volume goes up. And this is what we call Charles's law. So I said it before, but each of these examples, we didn't change the number of moles either. So we've got constant number of moles. So what if we keep the pressure and temperature constant temperature, constant pressure, and now we increase the number of moles, so we increase the number of particles. Well, we see the same thing happen again as with Charles's law, is that the volume gets bigger. So we've put more gas molecules in there now, so there's our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, let's say. We've increased the number of moles of gas in there, and again, we've got more collisions with the side of the container, so it's going to push the walls of the container out. we're going to see an increase in the volume. So volume is directly proportional to the number of moles, and this is what we call Avogadro's law, or sometimes it's called the Gay-Lussac law, depending on which historical experiment you're looking at. And there's one more as well, and we're going to look at this one only when we look at mixtures of gases, because what this law says is if we have constant volume, temperature, and total number of moles, but we change their identity, so we mix things up, so change the identity of the gases. And I apologize for the sloppy handwriting. It's very hard to write on the surface of an iPad very neatly. I know some of you can do it, so good work with that. So we're starting with our original container again. We're not changing anything about it except that we're replacing some of our molecules with different ones. So let's say we now have a mixture of two different gases in there. And what this law, what this observation was that doesn't change anything. So P total is unchanged, and I'll just put P total equals same. And in fact, it's just the sum of the pressures exerted by the two different gases. So the partial pressure of gas A plus the partial pressure of gas B. So this is Dalton's law of partial pressures. And we'll come back to this later again when we're looking at mixtures of gases. So the first three, this one, and this one, those all have to do with pure gases or mixtures. It doesn't really matter, but we've got a fixed total number of moles and we're not changing that around. We've got a fixed total number of moles in this one and this one. But we're not changing their identity. And then in the Dalton's law, we're changing the identity of the gas molecules. So maybe we're mixing different ones together. And so there's a nice slide that summarizes this information as well. And if we put all of this together, we see that volume is proportional then to number of moles and temperature, and inversely proportional to pressure. And if we want to make this an equality, V equals something, we just need a constant. So we can put some number in there, and I'm going to write it in the form that we're used to. And we'll put R, which is going to be our ideal gas constant. And that just allows us to take it from a proportionality to an actual equality. So nRT over P. And of course we can rearrange this into the form that we're most used to seeing, PV equals nRT, and that's where it comes from. So let's take a closer look at this equation and see what it tells us. So pressure times volume is essentially telling us an amount of energy. It's telling us an amount of expansion or compression energy available in a gas, and so we would call this the mechanical energy of a gas. Mechanical energy. And that's sort of equivalent to saying it's the amount of expansion compression work that the gas can do. Over here we have temperature, so this has something to do with the randomized kinetic energy of a gas. And so nRT, that term is basically what we call the thermal energy of a gas, or the heat energy within it. So all we're saying when we have PV equals nRT is that the mechanical energy a gas is capable of performing is equal to the thermal energy that it contains. So it could do an amount of work equal to the energy of the molecules bouncing around inside of it. So we better have units of energy on both sides, right? So we could have joules on both sides, or if we look at the more common units that we use for pressure and volume, the non-SI units are often liters for volume and atmospheres for pressure. And it turns out that 1 liter atmosphere, and I'm going to write it that way because that's the way we more commonly see it, 1 liter atmosphere, well, we can say that that's actually equal to 101.325 joules. And that equation, or that conversion factor, is on your equation sheet. So you can always look it up there if you need it. And so we could get units of energy that are either liter atmospheres or joules. Briefly, let me show you how a liter atmosphere equals this many joules. We'll do the derivation quickly. So if we write that 1 liter times atmosphere in SI units is 10 to the minus 3 meters cubed times 101,325 pascals. You can start to see where the 101,325 is going to come from. A pascal, 1 pascal equals 1 kilogram per meter second squared. Now, very important note, this is listed wrong on the equation sheet, so please make sure that you have this written down right in your notes, and I will fix it on the equation sheet before the exam. On the equation sheet, I think it says kilograms times meters per second squared, but it should be kilograms per meter per second squared. So that's 1 pascal. Then we can write that this is 10 to the minus 3rd meters cubed times 101,325 kilograms per meter second squared. So we get 101.325 kilograms meters squared per second squared, and that's just equal to 101.325 joules. So we see that the liter atmosphere is a unit of pressure equivalent to 101.325 joules. And then we've discussed it before, but our gas constant is just a conversion factor between units of temperature there and units of energy, because we want this whole thing to be in units of energy. So we've got temperature and say Kelvin or Celsius, but we want to convert it to energy. And so what it's really telling us, what R is telling us, is the energy content per mole of molecules per degree temperature that they contain, or per degree temperature that we are measuring. So it can have units of joules per mole per Kelvin or liter atmospheres per mole Kelvin. So it's going to be 8.3145 joules per mole Kelvin, or that's equivalent to 0.08206 liter atmospheres per mole Kelvin. And you're going to choose the units that are most convenient for the problem that you're solving. So if you have pressures and volumes in liters and atmospheres, you're going to use this R value. And if you have pressures and volumes in SI units, so this would be pascals for pressure and meters cubed for volume, then you're going to use R in the SI units. To keep these videos each very short, I'm going to go ahead and start a new video to work through examples using the ideal gas law. So we'll call the next video Ideal Gas Examples.